Hi again everyone, Chris Tisdale here again. In this presentation I'm going to start a new series of videos on vectors. And in particular, this video is going to be a completely introductory, very gentle presentation on basic introduction to vectors, what is a vector, and some of the geometric ideas associated with vectors. So you don't need to know anything about a vector to understand and follow along with this presentation. Now in other videos I'll do more advanced aspects, I'll cover more advanced aspects of vectors, but this particular presentation is just very elementary. So let me share my screen with you and let's get started. All right, so where are we going? We are going to discover new kinds of quantities called vectors. And we're going to learn the basic properties of vectors and also discover and investigate some of their mathematical applications. Now, a really good question before we begin is the following. Why do we need vectors? We don't know what they are yet, but what motivates the study of things called vectors? Well, vectors arise from the limitations of traditional numbers, also called scalars. Okay, by that, for example, real numbers. And let me give you a couple of examples to illustrate the limitations. So suppose you ask yourself, or we're asked, what is the current temperature? To measure temperature, we would use a single value, a single number, 25 degrees, for example. But if we ask the following question, things get a bit tricky. What is the current velocity of the wind? Now, you could say something like, I don't know, 10 kilometers per hour, but that information doesn't really cover the aspects that we're looking for. We not only need a speed, but we also need a direction. Okay? So it might be 10 kilometers per hour from the southwest. Okay? Now, to describe these more complicated cases and to answer these more complicated questions, we use vectors. Okay? Now, as I'm hinting at here, there are two reasons why vectors are awesome. Firstly, their applications. They give us a framework to model and describe lots of things around us, especially in physics, for example, where we're modeling forces, and engineering too. The second reason why vectors are awesome is because they have the ability to simplify mathematics in 2 and 3 and higher dimensions, including geometry. And we'll look at a little bit of vector geometry later in this presentation when I do an example. Okay, now here is a picture of lots of arrows in the plane, and you can see if I'm out here, the arrows are shorter than in here, and they all seem to be sort of pointing different directions depending on where I am in this picture. So this might be modeling the velocity of a wind or a circular wind or something like this. Okay. So now we get to the completely elementary part of this presentation. What is a vector? Well, I'm glad you asked. A vector is a quantity that has magnitude and direction. Okay, so by magnitude, we mean some sort of length, and by direction, we mean that it's pointing in some particular way. Now, geometrically, a vector can be represented by a line segment of a line which has a little arrow on it to indicate direction. So here is a vector. The one point is one endpoint of the line segment is at A, the other endpoint is at point B, and the arrow pointing towards B means the direction is in this direction. Okay, so this direction here. All right, so we would call this vector the vector AB, or the vector from A to B. Now I've just hand drawn in a whole bunch of other vectors just represented by directed line segments. You can see they all have a length. I can measure that length there, I can measure that length there, that length there, that length there, and they all have directions. Now if we just compare these handful of vectors here, if you measured the lengths of this, you'd see that these two vectors have the same length, but they're pointing in opposite directions. This red vector and this orange vector have the same length and they're pointing in the same direction. Okay, so these two vectors are actually equal to each other. This vector is pointing up here, this vector is pointing down here. They're certainly not pointing in the same direction. Now, even though these two vectors are pointing in opposite directions, they are still parallel to each other. Okay, these two vectors are parallel to, and they have the same length. All right, so you can also move vectors around. Okay, so I could move, copy that and move it up here and paste it in there. And as long as you don't change the length of the vector or the direction of the vector, then it's still the same vector. So think of taking this vector, copying it, pasting it over here. They are the same vector. Okay, even though one's in red and one's in orange, they're still the same vector. All right, a little bit on notation. There are lots of different ways of writing or denoting that something is a vector. You can use boldface notation, which distinguishes, say, the vector A from the number A where there's no boldface. This is hard to do with a pen and paper, though. So if we want to make things a little bit easier for a pen and paper, we can use a tilde. This is an under tilde. Or, as we have done up here, we can use an arrow to denote a vector A. If we're emphasizing the two endpoints, A and B, of a vector, then we can write this notation here, AB, with an arrow to signify the vector from the point A to the point B. Okay? Now, you'll see in this picture up here, A is what I call the tail point. Okay? And B is the head point. Okay? So if you think of this sort of arrow, this directed line segment, as having a tail point and a head point, then we can discuss a little bit about the geometry of things like addition and subtraction. Okay, so a vector has a length or a magnitude and a direction. That's pretty much all you need to know. Okay, and if you want to talk a little bit more, you have a head and a tail, or a head and a tail point. Okay. Now there is a really nice way of describing geometrically adding and subtracting two vectors, A and B. They use triangle laws and parallelogram laws. Okay, so let me discuss the cases here. Let's consider the middle case first. Now the arrows are kind of hiding here, so I'm going to just draw in the arrows. Now, even though I haven't drawn the arrow right at the end point, it's still hopefully you still get the idea. Okay, all right, so let's just concentrate on this middle point, the middle case for a second. Let's say I've got vectors A and B, and I wanted to add them together. What I can do in this picture is draw B, move B, so that the tail point of B starts at the head point of A. Okay? So if I do that, and then I draw a third line segment from the tail of A, or the tail point of A, to the head point of B, I actually get a triangle which is the sum of the two vectors. Okay, so here I've got my A, I've moved, my B might be over here, I've moved it in here, so the tail point of B and the head point of A are the same point. Okay, then what I do is I draw in a third line segment and I direct it from the tail point of A to the head point of B, and that is geometrically the sum of the vector A plus the vector B. Now, I don't have to put the tail point of B on the head of A. I could, if I wanted to, put the head point of B to the tail point of A. So you can see in this diagram here, just forget about the top triangle. Here I've put the head point of B to the tail point of A. And then I've drawn in another triangle there with a third line from the tail of B to the head of A. Okay, that's also geometrically the sum of the vectors B plus the vector A, or the vector A plus vector B. Okay, combining those two cases, you have two triangles. Okay, that triangle and that triangle are the same. And so that triangle and that triangle are the same, and that triangle is just sort of another half over here. This idea is called a parallelogram law. This idea is called a triangle law. Now, with the parallelogram law, you can also just draw your vectors like that. Draw another vector which is parallel, draw another vector which is parallel, and then join the corners of the parallelogram to get the sum. Okay, so here it is in words. You start with this side, and this side is the sides of your parallelogram, and this sort of diagonal forms the sum of the two vectors. Okay, if you draw your vectors from head to tail, and then you draw in your third side of your triangle, then that's also the sum of the two vectors. Now over here it's a little bit trickier because you've got subtraction. Okay. Well, basically subtraction is just the following. It's just addition applied to the negative of a vector. So what's the negative of a vector? Well, it's just the same vector but with the direction reversed. So if I draw in this line segment that's parallel to this vector here is negative b. So that's vector b there. This vector here is negative b. So if I apply my parallelogram rule or triangle rule, to this, I would go from the tail of this to the head of this, and that's why it's pointing this way. Okay. Now the only reason I'm putting double arrows on these sums is just to differentiate them from, you know, the A's and the B's. Okay, you don't have to do that. Okay, so hopefully you've got the idea now. Triangle rules are used for vector addition and subtraction, or you can use a parallelogram rule, whichever one you feel more comfortable with. Okay, so that's the geometry of adding and subtracting vectors. What about something like multiplying vectors together? Well, that's a little bit complicated for a first video. But what we can do is talk about, say, a vector and multiplying that vector by a number. Okay. Now, in the diagram here, here's a vector A. Here is 2A. Now, if you measure the lengths of this length and this length differ by a factor of 2. So this length will be exactly twice this length. Okay? Now if you look here, we've got A and negative A. This length and this length are the same, but again, let me just draw in the arrows to make them a bit bigger. So this length and this length are the same, but you can see that the direction has changed, reversed, or been twisted around 180 degrees. Okay, so if we are multiplying a vector, oh, actually I've got alpha there, so let me change that to alpha. Okay, alpha. A scalar alpha times a vector can stretch, or it can compress. If alpha was, say, a half, you would actually get something that was half the length, or flip a vector like we have in the negative case. If alpha is greater than 1, like we have here, the original vector is stretched. If alpha is between 0 and 1, say it was a half, the original vector would be compressed. If alpha is between negative 1 and 1, then the vector would be flipped and compressed. And if alpha is less than negative 1, the original vector would be flipped and stretched. So, for example, if you want to illustrate these cases here, draw in a half A, negative a half A, and say negative 2A, and see what happens. Okay. Now we've talked about adding and subtracting vectors, and earlier on I talked about a few vectors being parallel with some of the hand-drawn vectors that I drew in. Let's talk about parallel vectors, since we're talking about geometry. Two non-zero vectors u and v are parallel if there is a scalar lambda such that u is the product of lambda times v. Okay, so let's think about this. So let's just say draw in a vector u, and I draw in another vector, say up here. Well, clearly they're pointing in the same direction, and to get this vector, all you have to do is stretch this vector a bit. Okay, so let's make this, say, v. And I'm just going to use this. Okay, and to compute lambda, all you would do is you would measure the lengths and compare them and find the lambda that way. Now, secondly, we can use the idea of parallel vectors to distinguish whether or not 3 points are collinear or lie on the same line. Okay, so let me just draw in a line here. And suppose I've got following points, say A, B, and C, and we look at the vectors joining those points. Okay. Whoops, a little bit messy there. Sorry about that. Okay. Now you can see in this picture that AC is definitely a multiple of AB, so they're definitely parallel. Okay, so this then gives us a test to determine whether or not 3 points are collinear. Okay, what you would do is you would look at the vector, say AB, you would look at the vector AC, and you would ask yourself, are they parallel? Is one a scalar multiple of the other? And the important thing with this is that the vectors need to have some sort of point in common. Here they've got the point A in common. You could have the point B in common too. Okay, so let's do an example. Here I'm going to show you how to use vectors to prove a result from geometry. And in particular, this result and the ideas here involve the following triangles. So let's read the question and see how vectors can be used to solve it, to prove what they're asking us to prove. Now, the only real ideas that this example wants you to use are the following: the triangle rule or the triangle law for vector addition, the parallel properties of two vectors, and that's pretty much about it. Okay, so let's get down to the question. Consider the following diagram of triangles. So you've got one big triangle, you've got a smaller triangle inside the bigger triangle. Prove that the line segment joining the midpoint of the sides of the larger triangle is half the length of and parallel to the base of the larger triangle. Okay, so first of all, I'm going to label some things. So let A, B, C be the corners of the larger triangle, and let B, D, and E be the corners of the smaller triangle. Now we're told that this line segment here joins the midpoints of the sides of the larger triangle. So this length here and this length here must be equal. So that by putting these little sort of scores across the line segments, that's indicating that they're equal. Same over here. This line segment, the length of this and the length of this must also be equal. So I'm going to put 2 scores over there just to indicate that. Okay, so there's really 2 things that they want us to show in this problem. They want to show that this line segment is parallel to this to the base side, and that this is half the length of this. Okay, so how do we do it using vectors? Well, let me show you. We're basically going to show first that the vector from D to E is parallel to the vector from A to C. Okay, so what does that mean? That is, there is a number or scalar alpha such that DE equals lambda AC. And you can see from the drawing, since DE is smaller than AC, at least from the drawing, we would expect that the lambda here would be between 0 and 1, because you would compress AC down to get DE. Okay, so what I'm going to do now, I'm going to try to describe AC in terms of all the other vectors associated with the triangles here. Okay, I'm just going to use the triangle law of addition here. So, by the triangle law, vector AC, okay, is just vector AB plus vector BC. Okay, that's just the triangle law. This is this plus this. Okay, this vector AB plus the vector BC. Now, if you're ever unsure about this, you can also think about this algebraically. See the 2 inner B's? If you cover them up, what do you get? You get the vector AC. Okay, so that's an algebraic check to make sure that you're using the triangle in the right way, the triangle law in the right way. Okay, let's think about AB now. AB is the vector from A to B. Now that's just the vector AD plus the vector DB. All right, let's look at BC. BC is the vector BE plus the vector EC. Again, you can check that the inside letter cancels out if you cover them up, and you get the two vectors on top. Let me just sort of work around that. Okay, AD and DB. Well, there's AD, the vector AD. There's DB. Now, they have the same length and the same direction because we know that this length and this length are equal, and you can see that they lie on the same line segment. So these two vectors have got to be equal. Okay, so I can basically write one of these in terms of the other one. Which one's handier? Well, I could write 2AD there, but that doesn't really connect with DE in this sort of triangle way. So I'm going to write it in terms of 2DB. Same with BE and EC. This length is the same. BE and C are on the same line segment. So definitely the vectors BE and EC are parallel and they have the same length. So they must be equal. So again, I could write 2EC here, but I'm going to write 2BE because I can then combine it with the triangle inequality for the smaller triangle. Okay, so I can take a common factor out. All right, what is this? Well, cover up the B's, it's got to be the vector DE. DB plus BE equals DE. That's what we want to get down to. All right, so have we shown this? Have we shown there is a number lambda such that this is true? Yes, I have, because I've got the vector AC is 2 times DE, so if I rearrange that, I'll get DE equals half AC. Hence, DE is parallel to AC. All right, so that's the first part of the question. I've kind of squeezed it in there. What's the second part of the question? Second, well, basically, I've done that. I've done the second part first. I've done the parallel tube. I want to show that this length is half of this length, but that actually follows from what we have here. Okay. Let me show you. We have, okay, now I'm going to use the following notation to denote the length. So these sort of vertical lines are going to denote the length of the vectors. So if I take the absolute, well, the lengths of both of these line segments from here, I'll get the following. Okay. So what does that mean? It means the length of this vector is half the length of this vector. Or equivalently, the length of this line segment is half the length of this line segment. So line segment DE is half the length AC. Okay, and by these I just mean the line segments. Okay, so that is a basic proof using vectors. Okay, and only use things like triangle rule and a little bit of parallel vector ideas. Okay, so that is a very gentle introduction to vectors. Now, some of you may be thinking, but what is a vector? All you really need to know at this stage is that vectors have magnitude, length, and direction. Okay, and we can represent them as a directed line segment. Now, some of you are thinking, well, I know a coordinate way of writing vectors. I can write them in terms of the basis vectors, ij's and k's. That's okay, we'll get to that a bit later. Some of you may also be thinking, aha, a vector is just an element of a vector space. Yeah, that's a little bit advanced for what I'm doing in the introductory lecture. Okay, so join me again for the next installment in my series of vectors, and we'll talk a little bit more about vectors and what they are and what we can do with them. I hope you can join me then.